Hello, and welcome to Functions and Their Inverses. This is an intermediate algebra overview of the topic. Let's start with the definition. And my definition is an inverse function is a function that undoes another function. So it's kind of the opposite. In fact, the inverse takes any point x, y, and switches it to the point y comma x. All right, that's all it does. It switches x and y to y to x. Therefore, the domain of the original is equal to the range of the inverse, and the range of the original is equal to the domain of the inverse. Now, we're going to use two different techniques here. And we have a technique for finding an inverse in a real-world problem, and it's slightly different than just finding a generic inverse. So let's follow these instructions. First, we're going to write without function notation. And we'll see that in the example down here. And then we'll solve for the, quote, other variable. So the original input variable, we want it to become the new output variable that's isolated. We'll now rewrite in function notation and be cautious. We do not ever want to switch the variables in a real world problem, as they actually have meaning and units attached. Let's take a look at this example. To calculate the cost of to purchase custom printed lunch coolers for school staff, we use the function C of L equals 45 plus 3L, where C of L is the total cost in dollars for purchasing L lunch coolers. All right, we've seen this problem before. It's earlier in the playlist. I believe it's one of the first sections, really, when we start playing with things that are going on in linear equations. What are the input and output variables for this function? Our input is L, the number of lunch coolers. Whereas our output is C, and it's the cost of L lunch coolers. And in dollars, probably. It doesn't say that anywhere. Oh, there we go. In dollars. So it's in dollars. Now, to find the inverse of this function, our first step is we're going to write without function notation. So I'll call this C equals 45 plus 3L. All right, so that's step one. Step two, this is where all the work is. So I'm going to put a little star. This is where all our work happens. We're going to get L by itself. So let's subtract 45 from both sides and then divide by 3. And I'm going to divide this entire side by 3. Step 3, now we'll rewrite in function notation. So now L is a function of C, and that function is defined by C minus 45 all over 3. Now, what are the input values and the output variables, input and output variables for the inverse? Now the input is C, our cost, and our output is L lunch coolers. So we could use either the original function, C of L equals 45 plus 3L, or the inverse function, L of C equals C minus 45 over 3, depending on what we know and what we want out of it, right? The different outputs. So find the cost to to purchase 60 lunch coolers. Since we're using 60 coolers, if 60 coolers is the input, I'll use the original. The cost is 45 plus 3 times 60, which is 45 plus 180, and that is $225. Okay. Now find the number of lunch coolers you could purchase with a budget of, this time I know the money, so I'm going to use the inverse. The inverse tells me that I want to know the number of lunch coolers. If I have $300, my formula is 300 minus 45, so that's 255, divided by 3, and 255 divided by 3, we do have a calculator over here, but let's use a little bit of brain power. 3 goes into 24 8 times. With 1 remaining, bring down that 1. 3 goes into 15 5 times. So we could find we could buy 85 lunch coolers with a budget of $300. I'd probably take care of my entire department for sure, I think. A lot of times our secretarial staff will buy the faculty gifts for Christmas. And it's so weird and so appreciated. Okay, so a team of engineers, we're going to do this again. A team of engineers is trying to pump down the pressure in a vacuum chamber. They know that the following equation represents the pressure in the chamber. P of S equals 35 minus 0.07 S, where P of S is the pressure in pounds per square inch of a vacuum chamber after S seconds. Find the inverse. All right, so step 1 of the inverse, write it so it's not in function notation. My S's look a lot like 5s. So 5s have a nice cap lid to them, whereas the S does not necessarily. Second step, we're going to solve for the other variable. So I am going to subtract 35. And then I'm going to divide by a negative 0.07 to get S by itself. Dividing by this negative, we could kind of work with this, but I'm just going to leave it. I'm going to call this S of pressure. The number of seconds given the pressure is given by pressure minus 35 all over negative 0.07. Use the inverse function, so it tells us which one to use, to estimate the time it will take to pump down this vacuum chamber to 5 psi. So this is a pressure. I input a 5, so the number of seconds to come down to 5 psi is 5 minus 35 over negative 0.07. And this time, I'm going to use the calculator available. 30 divided by 0.07. Notice I didn't use the negative for either one of them. That's because I knew that a negative divided by a negative was going to be positive. So 428.57, we'll call that about 429 seconds. Remember, the output is time for the inverse function and the number of seconds. If the original function had a domain of 0 is less than or equal to S is less than or equal to 500 and a range of 0 is less than or equal to P is less than or equal to 35, what are the domain and range of the inverse? So I'm going to go with domain of inverse, and I'll put in parentheses range of original. That's 0 is less than or equal to P is less than or equal to 35, right? Because the pressure for the inverse, the pressure is the input. That's going to be our domain. Whereas the range of the inverse, which is the domain of the original, oh my goodness, I swear I know how to spell original. That's going to be 0 is less than or equal to S is less than or equal to 500. Okay, so all it does is switch X and Y in the definition. But for a real world problem, it's going to switch input, seconds, to become output. It's going to switch output, pressure, and that's going to become our input. And so the domain and ranges will switch as well. Now we could do this whole idea of finding an inverse with just a function without context. So there's no units, there might be units, but there's no meaningful variables associated with each of these inputs. And so we're going to use similar instructions. So step 1, we're going to write without function notation by replacing f of x with y. Then we'll solve for x. That's our original input variable. This will make a new, it'll be the new output variable. Then we're going to interchange x and y, and I'll be honest with you, sometimes I do these two steps in the opposite order, and it just kind of depends on which textbook I'm using, which course I'm teaching. 2 and 3 can be interchangeable there in our steps, but we always want to start with rewriting it as a y equals equation. And then I'm going to solve for x. So I'm going to use these steps because those are the ones written down in this lecture. Let's add 20 to both sides. And then let's divide both sides by 20. No, let's divide both sides by 4. There we go. Y plus 20 is divided. Step 2. Wow, that's where all the work is. Step 3. Y plus 20 divided by 4 is equal to x. Now step 3 says what was an x becomes a y. What was a y becomes an x. And this is the step we do not do in real world problems. We finish it off by using inverse function notation. And I make sure that whole x plus 20 is going to be divided by 4, so I had to extend my fraction bar there. And that's it. That's the inverse. That's our answer. Fantastic answer that it is. So let's try this again. Y equals 1/5 x plus 7. That's step 1. Step 2 is where all the work is. We're going to solve for x. So we'll subtract 7. And then let's multiply the right side by 5, because instead of dividing by 1/5, nobody really wants to choose to divide by a fraction if they don't have to. So let's just multiply by 5, and the reason for that is we'll have 5 times y minus 7 equals, and then the 1/5 times 5 makes 1x. As I take this up to the next line here, we want what was an x becomes a y. What was a y becomes an x. And you can leave it as y equals 5x minus 7, or you can distribute. It's always better, not better. It kind of depends on what it is that you're doing, which form you prefer. But to finish it off, we started with an f of x. We started with a function. We have to make sure we finish in function notation as well. And I personally would take either of those answers, 5 times parentheses x minus 7, or the simplified, or excuse me, distributed 5x minus 35. Factored form or not, it doesn't really matter. Okay, horizontal line test. A function in which each input corresponds to only one output and each output corresponds to only one input. This is the key right there. It's called a one-to-one function. So we know that each input can go to only one output. That's what makes a function. But now we're saying each output could only come from one input. And there's a specific reason why we want to do this. We use the horizontal line test in order to determine if a function, if a graph of a function is one-to-one. And so if you wanted to, you could use a graphing utility like Desmos. Currently doing some remote learning here at schools that I teach at. So Desmos is a great app to use. They have it for iPhones and Androids, PCs, Macs, everything. But I am going to use the graphing calculator I have right over here. So if we have 2x minus 5, we could take a look at the graph. F of x equals 2x minus 5. Notice this is a nice linear graph. It makes a nice straight line. Each x goes to only one y, and each y comes from only one x. So this function, y equals, f of x equals 2x minus 5. I'm going to do kind of a quick and dirty sketch, but maybe I won't use a highlighter for that. So this function is a bad representation of that function. I could do this. There we go. There we go. So this function is one-to-one. So let's look at g of x. G of x, I'm going to clear this first function out. I'm going to type it in exactly as it's written, 3 times parentheses x minus 2. A little vertex form going on for us. As we know, this is a parabola. Quadratic function has the shape of a parabola. And here we find that if we look at the graph, notice, I'm going to try to make this a little darker because, I don't know, black isn't dark enough. Notice that each x goes to only one y, but here's a y that has two different x values. Right? One y value comes from two different x places. So this is not a one-to-one function. We could keep trying. Let's do this one, 2.6. Throw down some parentheses, 1.8, close the parentheses to the power of x. Looking at that graph, an exponential function, we're going to take a much closer look at those in this section. We're going to talk about logarithmic functions as well. We know that an exponential function has the shape of, it's kind of always increasing or always decreasing. This particular one is always increasing. Notice for each x, there's only one y. And for each y, it comes from only one x. So it doesn't matter which y you choose, there's at most one x. So this is one-to-one. And finally, h of x equals -3. We can draw that graph. Here's -3. Each x has only one y. This is a function. However, this particular y value of -3 has an infinite number of x values that get you there. This one is not one-to-one. All right, so we're going to take a look more closely at one-to-one functions and what is not one-to-one. And as it turns out, any function that is one-to-one will have an inverse. It's guaranteed that it's going to algebraically have an inverse. So let's take a function like this crazy one we have up here. Part C. What I know about this one-to-one function, all right, this one-to-one function, since it has an inverse, I'm going to try to draw a straight line here. I failed twice. There we go. I know that its inverse will always be symmetric. Sorry, let me find the right words. Its inverse will always be symmetric with respect to the line y equals x. So if I have my original function f, f of x is 2.6 times 1.8 to the x. That's a one-to-one function. If I draw this line, y equals x, then the inverse function will be a mirror image across that line. So if I could fold across the blue dotted line, I would absolutely have a mirror image. This is the point 0, 2.6. Hard to read, but we find this point will be 2.6, 0. Now, if you want to know more about this whole idea of graphing the inverse and the function on the same set of axes, keep listening. It's coming up in a pretty close, I think, if not the next lecture, the one afterwards. So that's it for functions and their inverses. Thanks for listening.